SenseTime, and is a computer vision company, and it's really great company. And I learned a lot about deep learning in SenseTime. And during the time I worked in there, and I learned a lot how to train a deep learning models. And now today's topic is about sharing the experience of how to writing a reinforcement agent in OpenAI Gym, and it's quite fun, especially when you playing some games you are not really good at it, and then the marks you are not get really high, but the AI got much than you, and you pretty feel amazing about it. And that's why today I want to share how to write your own agent. And today we will not deep into the deep reinforcement learning, but we will slightly talk about the hyper concept about how you can be aware to speed up your training, and how to interact with the OpenAI Gym environment. And today's topic is about introduction of reinforcement learning. And my name is Holman, and you can find me through the GitHub and my website or email. And first of all, the last speaker talked about supervised learning, and maybe someone may ask, what is reinforcement learning? Maybe you guys do not have much about background of it. And reinforcement learning is slightly just the middle of the unsupervised with the supervised. And with supervised learning, just like the last speaker, they have a labeled data, and then you have an answer, and then try to make the computer associate with the input and output, right? And for unsupervised learning, and you feed the data, and then let the computer to find the relationship between the data or the cluster. And for reinforcement, it's slightly different, because for the question we have to solve is we cannot directly observe the answer directly. For example, we cannot label it an action right or wrong every time in every frame for an agent. And that's why reinforcement learning can slightly at the between in the unsupervised and supervised, because we slightly know the outcome we want to optimize. We want to get the marks as high as possible, but in the meantime, and we cannot know whether the action recurring act is right or not. And this is a big picture in every reinforcement learning problem. And basically, all kinds of agent is work like that. And especially when you program it, also have the same flow. And we have two important elements. First one is the agent. Is the AI we want to program it, want to train it, and the second part is the environment. Environment can be a simulator or an actual real problem. For example, it can be a traffic selection in the databases or request handler, and you can use those environment also. But for nowadays, I think playing with games is much more fun, and that's why today we will focus on this car simulated games, and how to program a simple agent for that. And for each time step in the environment, you will, for example, time t, and the environment will give you a current state. It can be any kinds of form. For example, it can be a vision type, or just a sensor records, and also give you some rewards. What mean rewards is a value to evaluate the action you have got in the past time step. For example, when you are in an agent, imagine you are a robot in a maze. Your task is try to maximize the food you catch in the maze, and you have to looking around, and then with a limited time, you want to get as much the food as possible. And each time you got the state is a vision of a robot to see the world. And the problem is you don't have a GPS. You cannot locate whether the environment how it is, and the only thing you can see in the world is the maze and the direction and how do you see the world. And it can be a block that it can be a blocked scene. For example, you have 3 types of action you can do it: left, right, and forward. And then the scene you can see just a wall, and then you have a row in the middle. And then for a human, you will know that just keeping moving forward will be the best action, because nothing can block you, no obstacle to block you. But for agent, you have to try and using a try and error basis to learn from the experience, or for the agent know that something blocked you, you cannot move in that direction. But how you can define it, it is based on a mathematical formula. You can evaluate how good to be that particular state. For example, the example what I used before is you have a block in the left and right, and you cannot move in left or right direction. And you know that if you going back to status, and you will get lower future rewards, because someone blocked you, and you have to spend more time and wasting your time to catching more rewards. And that's why how the agent to regret for choosing an action is the opportunity cost, not choosing the best action with current state. Which means if I choosing a left in the previous example, the opportunity cost I choosing left is the not choosing the forward to saving my time. And that's why the goal for a reinforcement learning is try to maximize the future reward. And we define it as a discounted reward, because in the future we know that somehow we can go to the final places and we got the highest mark. And for the kart racing contest, you maybe you can go to the goal. And that's why the goal for a reinforcement learning is with a action state action pair with the best action with every state. And we consider every reinforcement learning problem have a optimal policy. What means optimal policy is a perfect AI can choosing the right action with any kind of states. And we imagine that we have that kind of equation or the AI in a particular problem, and we try to make our own agent as close as possible to the perfect one. And we know that no one is perfect, and it's possible to loop all kinds of possibility. And that's why how we can model it and estimate it to the optimal policy is our tasks. And how we evaluate a optimal policy, we consider a optimal policy called a PyS dysfunction, and we assume that it's perfect with every state action pair. And how we the value can get it contains 3 components. First one is the function. You know how the state transitions. For example, when you're doing the example I said before, you have 3 actions, and then the forward nothing block you, and then the left right block you, and then you know that when you pressing left, you will go to another state. The state is determinate, and you know what will happen after you're pressing a state. But and the second component is the reward. After you're taking a particular action, the reward function we know. For example, when you're pressing a left, and then you know that someone blocked you, and then you know how the reward will gives you. But actually, in most of the problem, you cannot view all kinds of possibility and how the state can change, because it's too large, the state transitions, and the reward is some kinds of stochastic, it may be, and the environment, it can be continuously changed. And that's why for the state change function, is normally you cannot model it, and the reward function is also. But we can some kind of to estimate a function of the optimal policy. We try to make our own function as close as possible. That's what I said. And we call that it can be a Q function. It is a value function, or estimate the in particular state action pair whether it's good or not to choosing the action. And how we can update that kind of equation is using this update step. And this update step is really important. Is what I said is the how the computer agent to know how to regret of an action is about not choosing the best action with given state. That is opportunity cost, right? And we call that a TD error. What means TD error is a temporal difference between you expect the reward for a particular state and the actual you receive after you taking action. And we can model it with these particular parts. And that's really important and for how we can model the environment for the agent to keep learning from the experience. And now we already go through some basic fundamental equation, and we try to looking how we can program a simple agent in simulation world. And of course we cannot make our own robots to work around the world, but we can play in the simulated world. And openAI Gym provides a really great API for us, and it wraps up many kinds of environment of it. For example, some classical couple problem and some Minecraft problem, they also include, and some of that, for example, Pygame is really easy to work around it. And now we are going to a racing 2D game. In this game, you have 3 input. This is a Pygame environment: left, right, and left, right, acceleration, and brake. And the state of this problem is a visual images. As you see, just like they have a car and then a road, and how the reward system is looks like is when you trying to achieve a block, and then it will have a marks return it. It depends on the track length, and then if you just staying not going forward, and then you have some penalty on -0.1 in every frame. And then we'll go through the notebook. And in this example, we will talking about some objectives of how to using the OpenAI Gym API is how simple like that, and then if you program yours and how you can the main loop, how this and how you can interact with the world, and I will show you like that. And then I will show you a algorithm called Q-learning, and then I use neural network for this problem, and then some layers, and how I will show you how to update the agent with the update step, the TD error. And then this is the pseudocode for the Q-learning. And the main idea is just what I said, how to update the Q function, the function to estimate in particular state whether we want to go how the probability how we want to go to that particular step, particular states. And I also use a memories replay. And since the problem we use in this problem is using neural network, but neural network is really bad for a similar data fit in, keep training it, and that's why you will get very easy to in overfit situation. And how we can avoid it is using a memories replay. For example, you can imagine every time an agent work in around the world, and then it will save that particular state action pair and rewards into a brain, and then after a certain time of time, and then it will sample it randomly in the memory, sample it randomly in the memory. It can assume that we can sample the actual problem function in the Pi function, and it's helped to avoid the correlation between the frames fit into the neural network to avoid a overfitting. And I use Keras to help us to simplify the code, but you can rewrite easily in TensorFlow. But I think Keras is is better for the beginners to define the networks. And memory's capacity, I suggest as large as possible. In here I use 6,000, but I think larger memory can help to reduce the correlation between frames. And the discounted factor, and what I said is the value for an agent to regret is not choosing the best action, right? And then how we can know the best action for a particular state is we know that that particular action can go to that kind of state, right? And that kind of state can, the future will give us a more rewards. And that's why we model that with a discounted reward. For example, the first step we have one reward, and then with the discount factor 0.997, and then going forward in the future. And then we use that value network to model it. We know that at that particular state we're willing to go into that because the future rewards is much higher. And this is the main classes to define the network. Is similar with the traditional supervised learning. You train a classifier, you train a simple regression model, and then I think you can walk through with the other speaker, and then you will know how to construct your own reinforcement, own deep learning model. And then the memory is my implementation is slightly easy and simple, just a random sample from the memory, but you can use prioritize the sample. For example, you want to feed the data with a higher marks, and then you may let the agent to sim more the experience with particular higher rewards states. And then this is the main part for the interact with the environment. How we can define an environment in openAI Gym is just gym.make, and then the environment you really want to play. For example, you can choosing a Atari game, and then you just put the problem, and then you can make your own game already. It's really handy. And for the agent, how to interact with the environment is also really simple. Just environment.step, and then you the environment will return a state action reward pair to your computer, to your agent, and then you can feed those values back to your agent, and then the agent you can do your stuff. You can implement your Q table or Q network to make your agent to learn. And I have a tips on if you implement a DQN for memories replay. I suggest you using a multiple agent for initialize your memory, because your memory is with high capacity, and you take some time to initialize all kinds of filling all the memory capacity. And that's why using a flash and then for openAI Gym, I think is the best method for filling all the memories. And then the next example is Universe. Universe is an extension of a openAI Gym, and it provides some flash game and some browser interaction, and is really powerful and great library for us to program interact with the flash game. It provides much more environments than Gym does, and more realistic. And here is some flash game samples they provide us, and you can wrap your own flash game also. It use Docker and then put into a VNC server and then connect it. But the lowest level things you don't have to care. Universe will do it for you, and the only thing you have to care is whether your computer have the capacity to do multiple agent at the same time, and how your agent construct it, and model how you define it, and your algorithm how to do it. And the things you have to care is the such high level things. For the low level things with the interactive environment, openAI Gym and Universe will do it for you. And now we will go into a neuron race example. This example is a flash game, neuron race level 0, as I remember. And then the state it gives us is a browser scene, and I chop it with the game, and then I feed it into the neural network. And then the rewards they give us is whether you have moving forward, and then do you catch up the cons, and then it will give you some rewards mark. And this is the notebook for these questions, and the algorithm I use is A3C method. Is a more advanced effort compared to the DQN. And the main idea for this method is we don't use the memories replay anymore, because memory replay really consume memories, right? We have to save all the experience in the previous, and then is really RAM consuming. And then we can speed up the training time using multiple agents at the same time, just like you have multiple agents, and then you share the same brain, and then every agent have the experience, and then it will backpropagate in the central brain. It's really help to training the agent. And if you writing your own reinforcement agent, you can try to implement this method, and it's really help to reduce the time you are training, and is really great. And the architecture is asynchronous advantage arithmetic method, and it have two parts. At the previous one, we only have one agent and then a queue function. But for this particular method, we have two function output. One is policy function, which is determine what kind of action we have to do it, and then the value function is evaluate the policy network whether it's doing a great things, and then to criticize this. But we don't dig into the how we construct those two function, but I will show you how we can using Keras and TensorFlow to make such a complex network, and with the less pain. And this is the high-level graph for the A3C A3C method. You can see that they will spawn multiple agents, and then do the try to explore the environment for you. That's why the how we program it is slightly different. We separate the brain classes out from the agent, because it's much more complex, and we have to define our own loss function and how the graph backpropagate it into the central brain. That's why we separate it. And with Universe, the API is really handy. You just import Universe. It will import all those things, but you have to install Docker before you run it. And the hyperparameter is also the same, but I lower the FPS. I think that 10 FPS is enough for such problem. And the action I provide for the agent, I have three: left, right, forward, the combination left, right, and the forward. And this is a class to define the brain, and this is a no matter is a central brain or the worker brain is also the same. The main difference is the central brain is responsible for the backpropagation and try to learn from the experience from each worker. And we can build the network easily using Keras, but Keras do not provide us a low-level API for defining how we propagate the gradients, right? And that's why we have to build our own graph. And then Keras provides a really great API for us to using the raw TensorFlow API to define our graphs. And for the optimize, just when the agent already explore enough experience, and then it will put into the central brain, try to calculate the gradient, and then backpropagate with the brain, and then it will learn from that agent experience. And this is the main function for the threading, and you can see that it's really clean, and just the OpenAI gym and universe, although you are spawning different environment and you will consume all kinds of memories, but it will spawn a Docker container, and then the environment works in that container, and you really save in the memories. You just kill the container, and then I think Universe is great library for that. And with the rest of the time, I want to introduce some library for the training your own self-driving car agent. One is a Deep GTA 5. Is letting you to train your own agent in GTA 5, and it's really fun. I have tried some and write a simple agent before, but I think I have to spend more time to training a better agent. And this is some pictures. You can see that how the agent interact with the world. Normally, we don't use the full HD image for training the agent because the state is too high and it's really hard to train that. That's why we resize this to a really small images. But the environment provides a really realistic environment for us. And the next one is highly recommended is Euro Truck Simulator. Euro Truck Simulator provides a really realistic car simulator, a truck simulator control, and they have lots of control. If you don't like the library, provide us you can write your own telemetry to connect the Euro Truck Simulator. You just capture it with OpenCV. It's really handy. It's handy, but it's really fun. I think you can spend time on it. And this is let me see. Do I have time to show that? Oh, no. I think this is the end of my presentation. Thank you. Yes. For the car, for example, for the Box 2D racing game, the 2D one, the environment gives us is whether we already go to a block. You can see the track. They have a light boxes. I don't know whether you can find it, but there's a slight lighting box here. When the car catch one block, it will receive some marks. And for the neon lights example, it uses the cones, and whether you stay on the track also give and whether you move it forward to the goal, also a reward giving you back after you achieve something. But in my experience, I think the reward functions is really important. For example, for a simple couple problem, do I include it here? Yes. This is a couple problem. And if you give the agent with a -100 after you is dead, and it helps a lot to converge, and less time to let the agent finding out whether that state is willing to get to in. And that's why I think reward function is really important. For sometimes the environment may not give you really great penalty system. You can just rating it, and then the agent may be training much more better. Thank you. Your questions. Mm.
The machine being helped by observing the human players to have a few playthrough and sort of summarize the human actions and sort of get the basics of the rules.
Yeah, I can call that is a semi-supervised reinforcement learning. You can basically you just record how you drive, and then you can record the actions, and then you can backpropagate to the agent, and then let the agent experience learn from your experience, and then it helps you to converge. But there's one new paper is about AlphaGo Zero. I think everyone may saw that. It's proof that even in a Go problem, you can just use pure reinforcement learning to solve it, and it's really powerful. And residential net, it helps us to reduce the complexity in the gradient descent and helps it converge. And I think you can use pure reinforcement learning to solve most of the game problem if you really that problem is a MDP. If the problem is really MDP, I think you can do it like that. It's because even Go can do that. I think you can solve others.
Sorry, I mean, Go is a very complex game.
Yeah.
But some of the card pull is obviously quite simple.
Yeah.
So I mean, how do you sort of incorporate the human sort of experience with the reward function you mentioned earlier? It just doesn't seem to fit very well.
You mean when you try to let the agent learn from your experience how to do it? When you're playing the games, you also got the state action reward pairs, and you also got the changes. You just feed your experience back to the agent, and then let the agent learn from the temporal difference between your action and the rewards get after your do an action. And then I think it's also okay. And or you have a much more complex problem, you can slightly just in the model you have a branch, and then make it supervised. For example, you label it with particular cars in the scene, and then you make the computer learn how to extract the features from know that, oh, there's a car in there, and then you can make the training more effective. I, uh, most of the solution I use is value iteration. Yeah, and for the attack critic, I combine it combine value and policy network. Yeah. Oh, I like to use Exxon Greedy, and it's simple, and I think Epsilon Greedy is enough for that. But due to a limited time, I won't talk too much about the Epsilon Greedy, how it works. But I like to use Epsilon Greedy in most of the cases. Okay, I think that's the end. Thank you.
Thank you, Holman. And actually, it's about time for lunch. And for participants who purchase the patron tickets or the donation tickets, you could proceed to the counter to grab your own T-shirt and the calendar, which is outside of this lecture theater. And remember to bring along your personal belongings when you leave this room. And also try to bring along with the trash, like or litter that you've brought here, so that other users, other participants may have a clean environment. And see you back in 10 to 2, like 1 past 1:50, 50. Thank you.